Okay, so the question here is, show that as a particle moves along a surface, it moves in such a way that its kinetic energy is at its minimum. So there's a couple of things we need here to start with. We need to set up a couple of variables. So S equals arc length and T is time. That's the first thing we need to set up. And then our coordinates on the surface of this, we call it a sphere, is X, Y and Z. So we've got X, Y and Z. That's our coordinates. And we're going to enclose that in a function which we're going to call phi. Okay, so for the arc length, to know the arc length at any particular time, we need ds, so that's the derivative with respect to s, equals x dot squared plus y dot squared plus z dot squared, and that's with respect to time, so that's any time. Now we've got some notation here, z dot, x dot and y dot. Now if you've not come across that before, don't panic too much. It just means it's a parametric derivative of x, y and z. So for the parametrics for x, y and z, we've got x becomes x of t. So x becomes a function which is controlled by t. Same for the y and same for the z. And then for the derivatives of that, for example, for the x, to get the x dot, we've got dx, ds, and then by the chain rule, ds, dt, and then that will give us dx, dt, which in this term here, we'll just write that as x dot. Now you can substitute the x for the y and the z to get the same ones. I'm going to let you guys do that. And that's how we get to the parametric derivative of x dot. Okay, so the next thing we need is kinetic energy. So the formula for kinetic energy is given by energy equals, now this is an integral. So it's the half from t0 to t1. That's your parameters of integration. And then you've got x dot squared plus y dot squared plus z dot squared, and that's also dt. So you can see there's some similarities here in the formulas for either of them. Okay, so now how are we going to find these at the minimum? So what we need to do is, for the energy and the movement, we need to set both of them to 0. So our arc length, we're going to minimize it. So basically we want to set our arc length to equal 0. And the energy needs to be minimized as well with this parameter in mind. So we need to try and find a point where energy equals 1/2. Now we'll go from 0 to t. We'll call t our parameter from a standing start. And then x dot squared plus y dot squared plus z dot squared dt. We're going to set this also to 0. Okay, so now what do we do now? So now we need something using a Lagrange multiplier. So we'll use lambda as our Lagrange multiplier. Oh, let's just write that properly. Multiplier. So what we've got to try and do is set this as f. So f equals this formula here. So f equals 1/2 of x dot squared plus y dot squared plus z dot squared. That's our functional. And we need phi of whatever the function is inside. So we need to add the Lagrange multiplier with phi, and then for any one of the partial derivatives and so on as we find each part. So that's our original starting point. So we're going to call that now f bar. Okay, we need to set this to 0. So the formula we're going to need for that is lambda multiplied by the partial of x, y and z. So partial of phi, first of all we do x, and then we subtract that from the derivative with respect to t, because we're always respect to t here, so this is respect to t, i.e. respect to the time, and then we multiply that by our parametric derivative with respect to our f and set that to 0. So our functional f. Okay, so phi, lambda phi of x, so I'm going to leave that as it is, lambda phi of x, and the derivative with respect to f bar, the parametric derivative, that's just going to give us x double dot. So now that's the second derivative with parametrics, and that's now equaling 0. Okay, so now we need to try and get lambda, which is our Lagrange multiplier, on its own. So now lambda equals, take this x bar over to the other side, so x double dot over to the other side, and then divide it by phi of x. So that's our partial of phi with regards to x. So that will give us our Lagrange multiplier with regards to x. Now we can do the same for our y's and our z's. We just change the lettering in here to x's and y's. So let's just have a look at that quick. So let's just take this one off. We've still got this on the board up here. So lambda partial derivative with respect to y minus the derivative with respect to t of our y parametric derivative with regards to f bar, and set that equal to 0, and you'll get the same as this one in same form, except with the x's replaced with y's. So lambda equals y second parametric derivative with respect to the partial with respect to y, and you'll see the same with the other one. So lambda equals z double bar partial derivative of phi with regards to z, and then all of these will have the same value. So basically what we can finish off with is say that lambda equals second parametric derivative with regards to phi of divided by phi of x equals second parametric derivative divided by the partial of phi with regards to y, and then we've also got the second parametric derivative of z divided by the partial of phi with regards to z. And that's our solution, where we will find the minimum kinetic energy of a particle moving along the surface. Okay, now if you look on the description below, we'll have some more parametric derivatives with regards to geodesics, and we'll show some other things on there. Okay, thanks.